Hello everyone, welcome to Cyber Platter. This is a video on ISC Square CCSP to help you prepare for the certification. Today we will cover part 2 of domain 5, that is cloud security operations. So the agenda for today is to learn how securely we can operate physical and logical infrastructure of cloud environment. This includes configuring access control, local and remote access, that is KVM, control-based access mechanisms, RDP. We'll also learn about network configurations, VLAN, TLS, DHCP, right? How OS can be hardened using baselines, standalone hosts, clustered environment, and also about guest OS. The first topic is secure KVM access to physical hosts. KVM stands for keyboard, video, and mouse. One of the primary tasks that we face in building cloud data centers is ensuring that we have properly secured both local and remote access to the systems in those data centers. Protecting local access first requires strong physical security. It is important to remember that the security of systems absolutely depends upon preventing unauthorized individuals from gaining physical access to them. Once you have physical access to a system, gaining logical access becomes much easier. In a data center environment, servers do not have keyboards and monitors attached to them. Imagine if you had a rack of 50 servers, where would you put all these keyboards? And why would you want them? Instead, data centers use KVM technology. Like I said before, it stands for keyboard, video, and mouse. And KVM technology allows data centers to have a single hardware station that provides physical access to servers but can be easily switched between those servers by changing a software setting. It reduces the footprint of hardware while still providing administrators with physical access to that hardware when necessary. It's actually quite rare for a server administrator to visit a modern data center unless there's a hardware problem that requires physical work. Instead, administrators use some type of remote access, and those remote access mechanisms require added security. Just as we can use KVMs in person in a data center, KVMs also provide virtualized access to servers. Administrators may connect to a KVM and remotely control it to manipulate the servers on a rack. This technology should be used judiciously and reserved for cases where it is absolutely necessary because it is equivalent to providing physical access to the server. For added security, access to KVM devices should require a checkout process. A secure KVM prevents data loss from the server to the connected computer. It also prevents unsecure emanations. Two-factor authentication should be considered here, and all access should be logged and routine audits should be conducted. A secure KVM meets a lot of design criteria. A few of them will be discussed here. The first one is isolated data channels, secure data ports. These are located in each KVM port. These make it impossible for data to be transferred between connected computers through the KVM. Next one is tamper warning labels on each side of the KVM. These provide clear visual evidence if the enclosure has been compromised. Housing intrusion detection. This causes the KVM to become inoperable and the LEDs to flash repeatedly if the housing has been opened. Firmware. It cannot be reprogrammed, preventing attempts to alter the logic of the KVM. Tamper-proof circuit board. It is soldered to prevent component removal or alteration. Safe buffer design. It does not incorporate a memory buffer and the keyboard buffer is automatically cleared after data transmission, preventing transfer of keystrokes or other data when switching between computers. Selective Universal Serial Bus, that is USB access. It only recognizes human interface device USB devices such as keyboards and mice to prevent inadvertent and insecure data transfer. Push button control. It requires physical access to KVM when switching between connected computers. There are other methods as well to access physical hosts other than the KVM that we just discussed. One of those is console based access. Regardless of vendor platform, all VM management software offers a manage by console option. The use of these consoles to access, configure, and manage VMs offers an administrator the opportunity to easily control almost every aspect of the VM's configuration and usage. As a result, a malicious hacker or a bad actor can achieve the same level of access and control by using these consoles if they are not properly secured and managed. The use of access controls for console access is available in every vendor platform and should be implemented and regularly audited for compliance as a best practice. Another method of accessing physical hosts is through remote desktop protocol, that is RDP. RDP was developed by Microsoft to allow a user to connect to a remote computer over a network and allow that user to interact with the remote computer via graphical interface. RDP requires that a user employs RDP client software while the remote computer must run RDP server software. Though developed by Microsoft, RDP client and server software are available for Windows, Mac OS, and various flavors of Linux and Unix. As with any remote access method, RDP must be properly secured and monitored, especially when used to access critical systems. Many versions and configurations of RDP are prime targets of man in the middle, remote code execution, and various other attacks. Ensure that you are actively scanning and patching all systems and make sure to keep an eye out for critical RDP vulnerabilities and patches. RDP should be configured with role based access controls to limit privileged access, and you should carefully log and monitor all RDP access in your environment. Remote Desktop Protocol, that is RDP, is considered an insecure protocol and should only be used within closed or private networks. Do not expose RDP over the internet without VPN protection at a minimum. The next topic is virtual LAN, that is VLAN. It is a network concept. VLANs allow us to logically group together related systems regardless of where they exist on the physical network. If you look at the picture here, though the buildings are in different locations, users in the HR department all share a network that's separate from users in the marketing department and those in the IT department. We can use VLANs to connect people who are on different parts of the network to each other and also separate them from other users who might be physically close to them. The ability to isolate network traffic to certain machines or groups of machines via association with the VLAN allows for the opportunity to create secure pathing of data between endpoints. Although the use of VLANs by themselves does not guarantee that data will be transmitted securely and that it will not be tampered with or intercepted while on the wire, it is a building block that, when combined with other protection mechanisms, allows for data confidentiality to be achieved. VLAN communication. Virtual LANs extend the broadcast domain. That means that users on the same VLAN will be able to directly contact each other as if they were connected to the same switch. All of this happens at layer 2 of the network stack without involving routers or firewalls. Let's see what does it mean to say that VLAN workstations communicate with each other as though they were on a single isolated LAN. The first thing is broadcast packets sent by one of the workstations can reach all the others in the VLAN. Broadcasts sent by one of the workstations in the VLAN cannot reach any workstations that are not in the VLAN. Broadcasts sent by workstations that are not in the VLAN can never reach workstations that are in the VLAN. All the workstations can communicate with each other without needing to go through a gateway. Next is configuring VLAN. Network administrators must do two things to configure VLANs. First, they must enable VLAN trunking to allow switches in different locations on the network to carry the same VLANs. Second, they must configure each switch port to connect to the appropriate VLAN. Switching technology then takes care of the rest, creating logical VLANs that connect related users to each user and enforce network separation. Now let's see how can we increase VLAN related security. We can do that by enabling VLAN pruning, that is removing unused VLANs, and we can also increase VLAN related security by disabling unnecessary protocols on switches. The next topic is Transport Layer Security (TLS). TLS is a cryptographic protocol designed to provide communication security over a network. It uses X509 certificates to authenticate a connection and to exchange a symmetric key. This key is then used to encrypt any data sent over the connection. The TLS protocol allows client-server applications to communicate across a network in a way designed to ensure confidentiality. The TLS protocol replaced the long-used SSL Secure Sockets Layer protocol, which has since been deprecated. As such, TLS is now the de facto standard for encrypting network traffic. TLS is made up of two layers. The first one is TLS record protocol. This provides the actual secure communications method for data in transit. TLS record protocol ensures data confidentiality by encrypting the connection with symmetric key encryption and validates data integrity through the use of hashes and checksums. It is used to encapsulate various upper layer protocols, most notably the TLS handshake. The second layer of TLS is TLS handshake protocol. This allows two parties like a client and server to authenticate each other and negotiate the parameters of the TLS connection, including the session ID and encryption algorithms to be used. The entire handshake process occurs before any secure data is transmitted. The next topic is DNS. Domain Name Service. Computer uses IP addresses to communicate over the network, but those addresses are very difficult for people to remember. Just try to imagine how hard it would be if you had to memorize the IP addresses of every web server that you usually access. The Domain Name Service or DNS allows people to use easily recognizable names in place of IP addresses. DNS servers translate the names that you are more familiar with, such as www.google.com, into the IP address that computers use to communicate. The DNS works as a network service that operates over UDP port 53. Every time you connect to a network, that network provides your computer with the IP address of a local DNS server that it can use to look up other IP addresses. Then, whenever you type the domain name of a website into your browser, your computer sends a request to the local DNS server asking it for the IP address associated with that name. If the server knows the answer to your question, it simply responds to the request with the IP address, and then your web browser can go ahead and connect to the website using that IP address. If the local DNS server does not know the answer to your question, it connects other DNS servers to determine the correct answer and then responds to you. DNS is a hierarchical and decentralized naming system. Most of the time, DNS queries happen behind the scenes and users never see them. Now let's see how we can make DNS more secure. DNSSEC is a suite of extensions that add security to the domain name system, that is DNS protocol, by enabling DNS responses to be validated. Specifically, DNSSEC provides origin authority, data integrity, and authenticated denial of existence. With DNSSEC, the DNS protocol is much less susceptible to certain types of attacks, particularly DNS spoofing attacks. If it is supported by an authoritative DNS server, a DNS zone can be secured with DNSSEC using a process called zone signing. Signing a zone with DNSSEC adds validation support to a zone without changing the basic mechanism of a DNS query and response. Validation of DNS responses occurs through the use of digital signatures that are included with DNS responses. These digital signatures are contained in new DNSSEC related resource records that are generated and added to the zone during zone signing. DNSSEC also prevents pharming attacks, that is, fake websites website credential harvesting. It also helps protect against volume-based attacks that compromise availability. Now let's see what are the threats to the DNS infrastructure. The first one is footprinting, the process by which an attacker obtains DNS zone data, including DNS domain names, computer names, and IP addresses for sensitive network resources, is called footprinting. Denial of service attack is when an attacker attempts to deny the availability of network services by flooding one or more DNS servers in the network with queries. Data modification, an attempt by an attacker to spoof valid IP addresses in IP packets that the attacker has created. This gives these packets the appearance of coming from a valid IP address in the network. With a valid IP address, the attacker can gain access to the network and destroy data or conduct other attacks. Redirection is when an attacker can redirect queries for DNS names to servers that are under the control of the attacker. Spoofing is when a DNS server accepts and uses incorrect information from a host that has no authority giving that information. DNS spoofing is in fact malicious cache poisoning where forged data is placed in the cache of the name servers. VPN, Virtual Private Networks. VPNs provide two important network security functions to IT administrators. First, they allow the secure interconnection of remote networks, such as connecting branch offices to a corporate headquarters or each other. This is known as site-to-site VPN. Second, they provide mobile workers with a mechanism to securely connect from remote locations back to the organization's network. This is known as a remote access VPN. VPNs work by using encryption to create a virtual tunnel between two systems over the internet. Everything that enters one end of the tunnel is encrypted and then it is decrypted when it leaves the other end of the tunnel. From the user's perspective, the network appears to function normally, but if an attacker gains access to traffic between the two secure networks, all they see is encrypted information that they can't read. VPNs require an endpoint on the remote network that accepts VPN connections. Many different devices may serve as VPN endpoints, such as firewall, router, server, or dedicated VPN concentrator. All of these approaches provide secure VPN connections, but organizations that have high volumes of VPN use often choose to use a dedicated VPN concentrator because these devices are very efficient at VPN connections and can manage high bandwidth traffic with ease. If we don't have a high volume of VPN traffic, we can choose to use the firewall, router, or server approach. If we go that way, we should be aware that VPN traffic requires resource-intensive encryption, and unlike VPN concentrators, firewalls, routers, and servers usually don't contain specialized hardware that accelerates encryption. Using them as VPN endpoints can cause performance issues. For many years, most VPNs used a protocol called IPSec, Internet Protocol Security, to create these encrypted tunnels. IPSec VPN works at the network layer of the OSI model. It provides robust secure transport, but it's often difficult to configure and may be blocked by firewalls. For that reason, IPSec is often used for static site-to-site VPN tunnels but is becoming less common for remote user VPNs. Remote user VPNs now often rely upon transport layer security (TLS) connections that work at the application layer. These VPNs work on any system with a web browser and use port 443 for communications, a port that is typically allowed through almost every firewall. When implementing a remote access VPN, administrators must choose from two different tunneling approaches. In a full tunnel VPN, any network leaving the remote device is sent through the VPN back to the home network and protected by encryption. This includes not only traffic headed back to the corporate network but all web browsing and other activity as well. The alternative is to use a split tunnel VPN. In this approach, some traffic is sent through the VPN while other traffic is sent out through the user's local network. The routing policy is set by the VPN administrator. In most cases, administrators configure the split tunnel to send traffic headed for corporate systems through the VPN while allowing regular internet traffic to go directly to the destination over the local network. This approach was set up to reduce the burden on VPNs and conserve bandwidth. Today, most security experts recommend against the use of split tunnel VPNs. End users generally don't understand the difference and assume that if they connect to a VPN, all of their network traffic is secured. This provides them with a false sense of security because some of their traffic is actually being sent directly over the internet and may be subject to eavesdropping. Another emerging trend is the always on VPN. In this strategy, all corporate mobile devices are configured to automatically connect to the VPN whenever they are powered on. This takes control away from the end user and ensures that traffic leaving the device is always protected by strong encryption. Virtual private networks provide administrators with the ability to secure otherwise insecure communications and create a private network using inexpensive internet connections. IPSec, Internet Protocol Security. IPSec uses cryptographic security to protect communications over IP networks. IPsec include protocols for establishing mutual authentication at the beginning of the session and negotiating cryptographic keys to be used during the session. IPsec supports network level peer authentication, data origin authentication, data integrity, encryption, and replay protection. IPsec may be a valuable addition to the network configuration that requires end-to-end security for data while transiting a network. The deployment and use of IPsec has two challenges. Configuration management. The use of IPsec is optional. As such, many endpoints connecting to the cloud infrastructure do not have IPsec support enabled and configured. If IPsec is not enabled on the endpoint, then depending on the configuration choices made on the server side of the IPsec solution, the endpoint may not be able to connect and complete a transaction if it does not support IPsec. Cloud service providers may not have the proper visibility on the customer endpoints or the server infrastructure to understand IPsec configuration. As a result, the ability to ensure the use of IPsec to secure network traffic may be limited. The next challenge is performance. The use of IPsec imposes a performance penalty on the systems deploying the technology. Although the impact of the performance on an average system is small, it is the cumulative effect of IPsec across an enterprise architecture end to end that must be evaluated prior to implementation. IPsec operates in one of the two modes, tunnel or transport. Tunnel encrypts the entire original packet and provides a new header. It supports NAT traversal. Transport only encrypts part of the original packet. The next concept is DHCP, Dynamic Host Configuration Protocol. DHCP is a protocol that assigns and manages IP addresses, subnet mask, and other network parameters to each device on a network. Without this technology, administrators must manually configure network settings on every device under their control. It's easy to imagine how such manual network configuration would be a challenge in large distributed cloud environments. So as you can see, this can be really helpful in a cloud environment and can help securely automate orchestration and configuration of networks. Because DHCP allows central configuration of critical network parameters, it is essential that all DHCP servers are tightly secured and controlled. Failure to adequately protect these systems can allow an attacker to manipulate IP addresses and network settings to redirect traffic to malicious or compromised destinations. The next topic is OS hardening with baselines. Most enterprise security teams are responsible for maintaining the security of thousands of devices ranging from laptops and tablets to routers and firewalls. The sheer number of these systems makes it impossible to manually configure each of them to operate in a secure manner. Security baselines provide enterprises with an effective way to specify the minimum standards for computing systems and efficiently apply those standards across deployed devices. Many organizations begin their security standardization efforts by developing a baseline standard that sets forth the minimum standards that apply to all devices, regardless of their purpose, operating system, or the types of data that they contain. For example, a baseline security standard might require that a named individual is responsible for the security of each device, that the device is protected against unauthorized access attempts, that it does not jeopardize the confidentiality, integrity, or availability of other systems or the data they contain, that the device remains under the positive control of trained system administrators, and that all activities on the device comply with data security requirements. Now, those requirements sound pretty generic. That's actually the point of the baseline security standard. It sets forth a clear set of minimum requirements that apply to every device in the enterprise. They are especially useful during the countless times security teams come across a new type of device that is joining the network. Even if there is not specific guidance in place for that type of device, administrators can turn to the security baseline to determine the generic controls that should be in place. Baselines can also dive into deeper detail, breaking out different requirements for different classes of systems and information. An organization might identify their security baseline controls based upon the highest classification of information stored, processed, or transmitted by the system. For example, the security baseline might require that all data storage devices be encrypted when they are used to store highly sensitive information. In addition to the baseline requirements, organizations often create specific security standards for the operating systems, mobile technologies, network components, appliances, and other systems commonly used in their environment. These standards describe how the organization will specifically achieve the baseline requirements on a particular system type. For example, the baseline security standard for a Windows system might require that the system's host firewall be enabled with all ports blocked other than those specifically required for specific business purposes and documented in a network access approval. Security baselines often require hundreds or thousands of individual security settings on a particular device. If administrators try to configure these systems manually, they quickly find that it is an impossible task. There are simply too many settings and too many systems to configure. Fortunately, automation technologies are available to rapidly deploy configuration templates across a large number of systems. For example, administrators can create a standard configuration template for all end user Windows systems and then apply that template across all systems through the use of group policy objects and Active Directory. Configuration management tools such as Puppet and Chef can ensure operating systems are hardened according to a given baseline or policy. Once administrators set baseline requirements and deploy those baselines across the enterprise, they should continue to monitor systems for compliance with the baseline. Users might accidentally adjust settings. Administrators may make errors in group policies. Attackers might undermine security, or any other activity might cause deviations from the baselines that require remediation. Automated monitoring solutions allow administrators to rapidly check thousands of systems against the baseline and identify any deviations that require investigation. Security standards may contain hundreds or even thousands of individual settings that experts recommend to improve system security. While these settings are important, most organizations simply don't have the resources or expertise to develop their own standards. Fortunately, vendors and third party security organizations develop and create industry standards that may serve as the starting point for enterprise security efforts. One of the most common sources of security standards are the vendors who create devices, applications, and operating systems. Example, the Microsoft Security Compliance Toolkit helps with system configuration and management. The US government also spends quite a bit of time and energy on security standards, and the National Institute of Standards and Technology, or NIST, is an excellent source for security guidance. Some organizations want an even more objective objective source than the government and seek out third-party organizations that exist solely to provide security advice. For example, the Center for Internet Security provides a series of security benchmarks that represent the opinions of a series of subject matter experts. Windows. Microsoft offers several tools and resources to support baseline configuration and management. Endpoint Configuration Manager, Intune, and Microsoft Deployment Toolkit (MDT) all offer tools and processes for automating and deploying system configurations. Especially, Microsoft Deployment Toolkit (MDT) enables you to deploy and manage system images and can be used to help you manage initial and ongoing security configurations of your baseline images. Linux comes in many different flavors and distributions, and each includes its own set of default utilities and settings. As such, your process for creating secure baselines largely depends on which flavor you are using. Some Linux variants are offered as bare bones distributions that come with very few processes and utilities. These distros may require minimal hardening, whereas some of the other more robust Linux distros may need to be heavily modified and restricted depending on your particular use case. All in all, when establishing and applying baselines for Linux, you should first start with general Linux guidelines and best practices before moving on to vendor specific guidelines and recommendations. VMware is a historical leader in virtualization and cloud computing. VMware has developed its operating systems with remote and automated baseline management features built in. VMware's vSphere Update Manager (VUM) utility allows you to create and manage host baselines, virtual machine baselines, and virtual appliance baselines all in one. VUM provides insights into your entire vSphere OS deployment and allows you to quickly identify and fix hosts that are not compliant with their respective baselines. The tool can also help ensure that all systems under a given baseline have been patched and received any other security configuration updates. The security standards offered by industry experts are an excellent starting point for an organization's own security standards, but they are rarely ready to use out of the box and often require customization to meet the organization's specific security requirements. Organizations often start with these baselines and then add, remove, and modify controls to develop their own security standards. The purpose of these customization efforts is to scope and tailor the standard to meet the organization's specific needs. For example, an industry standard might suggest using full disk encryption to protect storage data on an endpoint and suggest the use of AES encryption with a 128, 192, or 256-bit key. The organization might have a compliance requirement that mandates the use of 256-bit keys. In this case, the organization might modify the standard to require the use of a 256-bit key, removing the option for a 128 or 192-bit alternative. The easiest way to document these changes is to write a security standard that references another standard. Any customizations that enterprises make to security standards should tie back to clear security or business requirements. These should include descriptions of the impact of the change on the confidentiality, integrity, and availability of systems, and information or the impact on compliance with other requirements. Organizations might also apply specific configuration standards to high value assets. This may mean requiring more strict controls on certain systems and data elements based upon the sensitivity of data or the criticality of a system to business operations. Now let's see what is a standalone host. Within a computing environment, a standalone host is a physical machine that operates independently from other machines in the environment. Okay. Most commonly, it is the business requirement that dictates the need for standalone hosts in a cloud environment. The business might want to create isolated, secure, dedicated hosting of individual cloud resources. For this, a standalone host is the appropriate choice. Yeah. The business might also want to make the cloud resources available to end users so they appear as if they are independent of any other resources and are isolated. Here we can use either a standalone host or a shared host configuration that offers multi-tenant secure hosting. So cloud service providers generally make standalone hosts available to customers who want to streamline their cloud migration. By offering standalone hosts, customers are able to maintain their existing system architectures and configurations as they move everything to the cloud. Another great use case for standalone hosts is in providing physical separation between systems or data sets, often for compliance purposes. So to summarize, standalone hosts advantages are isolation, dedicated host. It is more secure because it is not multi-tenant. Standalone host disadvantages are lack of clustering benefits, higher costs, and lack of elasticity. Now let's see the driving factors for the use of standalone hosts. As regulatory issues, the second one is current security policies in force, any contractual requirements that may be in force for one or more systems or areas of the business, the needs of a certain application or business process that may be using the system in question, classification of the data contained in the system, the performance of the system, right? Now let's see what is a clustered host. A clustered host is logically and physically connected to other hosts within a management framework. So why is this required? This is usually to allow central management of resources for the collection of hosts, applications, and VMs running on a member of the cluster to failover or move between host members as needed for continued operation of these resources, with a focus on minimizing the downtime that host failures can cause. Within a host cluster, resources are allocated and managed as if they were pooled or jointly available to all members of the cluster. The use of resource sharing concepts such as reservations, limits, and shares may be used to further redefine and orchestrate the allocation of resources. Reservations guarantee a minimum amount of the cluster's pooled resources be made available to a specified VM. Limits guarantee a minimum amount of the cluster's pooled resources to be made available to a specified VM. Shares provision the remaining resources left in a cluster when there is resource contention. Specifically, shares allow the cluster's reservations to be allocated and then to address any remaining resources that may be available for use by members of the cluster through a prioritized percentage-based allocation mechanism. The next concept is distributed resource scheduling, DRS. All virtualization vendors use DRS in one form or another to allow for a cluster of hosts to provide highly available resources to your workloads, balance workloads for optimum performance, scale and manage computing resources without service disruption. Using the initial workload placement across the cluster as a VM is powered on is the beginning point for all load balancing operations. This initial placement function can be fully automated or manually implemented based on a series of recommendations made by the DRS service, depending on the chosen configuration for DRS. Some DRS implementations offer the availability to engage in ongoing load balancing once a VM has been placed and is running in the cluster. Yeah, this load balancing is achieved through a movement of the VM between hosts in the cluster to achieve or maintain the desired compute resource allocation thresholds specified for the DRS service. The movements of VMs between hosts in the DRS cluster are policy driven and are controlled through the application of affinity and anti-affinity rules. These rules allow for the separation of VMs across multiple hosts in the cluster or the grouping of VMs on a single host. Grouping is by affinity rules and separation is by anti-affinity rules. The need to separate or group VMs can be driven by architectural, policy and compliance or performance and security concerns. The next concept is dynamic operation. Dynamic operation is the automated process of constantly reallocating cloud resources to ensure that no physical host or its resources become overutilized while other resources are available or underutilized. Dynamic optimization technologies use sophisticated algorithms and resource analysis to intelligently optimize resource utilization, reducing waste and cost while improvising service availability and performance. Dynamic hosting is one of the fundamental technologies underlying the fundamental cloud principles of autoscaling and rapid elasticity. The next concept is storage cluster goals. Before that, we'll understand what is a storage cluster. A storage device will be clustered in groups, providing increased performance, flexibility, and reliability. The goals of storage cluster include meet the required service levels as specified in the SLA, provide for the ability to separate customer data in multi-tenant hosting environments, securely store and protect data through the use of availability, integrity, and confidentiality mechanisms such as encryption, hashing, masking, and multipathing. Clustered storage architecture. Tightly coupled architecture. In this, all the storage devices are directly connected to a shared physical backplane, thus connecting all of them directly. The concept of tightly, right? Each component of the cluster is aware of the others and subscribes to the same policies and rule sets. A tightly coupled cluster is usually confined to more restrictive design parameters, often because the devices might need to be from the same vendor in order to function properly. Although this may be a limiting factor, a tightly coupled architecture will also enhance performance as it scales. The performance of each element is added to the overall performance of the cluster, allowing greater and greater power as it increases in size. The next one is loosely coupled cluster. A loosely coupled cluster, on the other hand, will allow for greater flexibility. Each node of the cluster is independent of the others, and new nodes can be added for any purpose or use as needed. They are only logically connected and don't share the same proximate physical framework. So they are only distantly physically connected through communication media, the concept of loosely. Performance does not necessarily scale because the nodes don't build on one another, but this might not be an important facet of the storage architecture since storage commands and performance requirements are fairly simple. The next concept is maintenance mode. Continual uptime requires maintaining the overall environment constantly. This also includes maintaining individual components both on a scheduled basis and at unscheduled times as necessary. The operational modes of data centers can be perceived as two categories, normal and maintenance mode. Realistically, the data center taken holistically will constantly be in maintenance mode as ongoing maintenance of specific systems and components is necessary for continuous uptime. Therefore, a cloud data center can be expected to be considered in constant normal mode with various individual systems and devices continually in maintenance mode to ensure constant operations. Now let's see what are the tasks that need to be done when a system or device is put into maintenance mode. The first one is all operational instances are removed from the system or device before entering maintenance mode. We don't want to affect any transactions in a customer's production environment. We therefore must migrate any virtualized instances of the specific systems and devices where they might be hosted before we begin maintenance activities. The next one is prevent all new logins. We don't want customers logging into the affected systems and devices. The next one is ensure logging is continued and begin enhanced logging. Administrative activities are much more powerful and therefore comes with more risk than the actions of common users. So what we should do here, we should log admin activities at a greater rate and level of detail than those of users. Maintenance mode is an administrative function, so the increased logging is necessary. Also, remember that before we move a system or device from maintenance mode back to normal operation, there are certain things that you need to do. Like you have to make sure that the device or system has all the original functionality necessary for customer purposes. You have to make sure that the maintenance was successful, and also make sure to properly document all the activity. So this is the end of part 2 of domain 5, cloud security operations. I'll see you in the next video. Take care of yourselves till then. Thank you so much for watching. Bye bye.